think we can get started. And today is our great pleasure to have Dr. Dongzi Li to visit our ASIAA and give us a talk here. And Dr. Li currently is a Sherman Fairchild postdoc fellow at Caltech. And before joining Caltech, she worked with Wiley for her PhD at the University of Toronto. And before the PhD program, she did her master at the University of Washington, Canada. And before that, she did her undergraduate at Nanjing University in China. And she grew up at Wenzhou, China. And this time is her first time to visit Taiwan, so let's welcome her.
It was my great pleasure to visit here. Ever since I come here, I have this trouble of eating too much. And my stomach is much more tired even than my brain. And so it's my great honor to talk about fast radio burst. It's a very new and lively field. But before talking about fast radio burst, I have to explain radio because there's lots of people doing millimeter radio things. So here, when I'm talking about radio, I refer to centimeter wave. And so the telescope in the centimeter wave is quite different because it's much easier to build it. You only have to be accurate up to the level of 0.1 wavelength. So in 1963, we already had this gigantic telescope at 300 meter arc single, which is basically the size of a valley. And now you can guess what is currently the biggest telescope, which you probably have heard about it. And it's fast in China, very proud. And it's 500 meters, completed in 2016. But you can clearly see, like in 53 years, it's only going from 300 to 500, and it's already the size of a mountain. It's really difficult to improve this way in terms of sensitivity. So in the recent years, the radio wave are going in a different direction because computing, well, it's not very clear here, but this is the money per operation. Well, the money dollars per what is this? Sorry, dollars billions of computation per second is increasing dramatically. So in the recent year, I think it's more in the development of interferometer. Yeah, you as people here might have this great honor to join with this very nice experiment we'll talk about later. But for example, this is an example of interferometer, which is CHIME in Canada. It has 4 cylinders. You probably hear talk from maybe. It has 1024 receivers and 1024 digital beams, and each beams are the combining the signals from all the 1,000 receivers, and they're scanning the sky all the time. So the raw data rate is really large, and the real-time search is really computational heavy. So that's why it's hard to do that in the early time, even if people have this concept. It only has to reach certain time. Now people finally has the chance to do this kind of experiment. And you can see the advantage of this that it has very large field of views. So this is the irreversible and flux. They have tiny minute field of views. And for fast radio bursts, things like you can see it 1,000 per sky per sky per second. If you only have less than 1 square degree field of view, it takes hundreds of hours of observation to detect one. So you really need a large field of view, and that's why this field previously doesn't exist and now exists. And so we are very lucky. We don't have to be much smarter than everyone else because it's sort of unexplored. So the discovery of FRB was in 2007, very recent. We found that in hundreds of hours of archival data. And it was quite exciting because this burst, you can see this black line is the FRB, and the x-axis is time, y-axis is frequency. The higher frequency arrived first and lower frequency arrived later. It's the whistlers, if you're old enough to know that. So the time delay tells you the total the first time they detected, they already realized that the amount of electron far exceeds the amount of electron you will see at that line of sight in our Milky Way. So in order to get this extra electron, they started to guess, oh, this one must have been from a cosmological distance. And that's exciting because it could be a new cosmology probe. So whenever you detect one, it tells you the total electrons from that line of sight. And you have all those detections and you can map the electron distribution in the universe. And this is detected in 2007, but the search is like search for this millisecond radio burst. It's not new, but at that time people don't have this. Even in 1980s, they actually have a detection towards M87, a galaxy that looks almost like FRBs, but follow-up of that, hundreds of hour follow-up of that, people didn't see it repeat, and people gradually lose interest of that. But it is nowadays like you have very good instrument that actually really boosts the field. So this is the detection from different telescopes. You can see it ever since the time starts to operate. You can't really see the color bar from other telescopes. So it's really, that's why it's very lively and exciting time. So China published this paper in 2021, and now it's entering a time you can do statistics about FRBs. So now with like more than 600 published FRBs, what do we know about it? There are lots of properties we know, like morphologies and things. Those are complicated and confusing. Things I find most constraining is, first, it has to reach a spectral energy up to 10 to the 35 percent per hertz. So instantaneously and per second per hertz, whatever progenitor it is, it has to provide a very large energy. And the second is the volumetric rate. So whatever progenitor it is, it has to be well populated to at least have enough source to explain this rate, which I will talk about later. And there are a few direct evidence about the progenitors. One is the discovery of the first repeater. So initially, when people first see FRB, they use telescope to follow up for hundreds of hours, didn't see it repeat. But this is the first time they stare at the source, and the source flares again. So if it doesn't repeat, it could be some catastrophic events like merging, like neutron-star merger or something. And you can imagine that there's some procedure it can produce large energy. But it has to repeat, so it has to survive. Now the first repeater has been active for 10 years and still remains as active as before, means that the age has to be greater than 100 years for it to doesn't show any difference in 10 years. So that's one clue, and at that time, like neutron star already started to become popular, like progenitors. And another very important direct evidence is the detection of an FRB-like burst from a galactic magnetar in 2020. Well, that's very straightforward. So this is the plot from the paper. The x-axis is the duration of the burst. The y-axis is the spectral luminosity. So this group is the FRBs previously seen. And this is the pulsar in our Milky Way, which energy is 7 orders, at least 7 orders of magnitude lower. And these stars are the magnetar bursts. So really, it's you don't need a lot of interpretation. You're already saying, oh, this is clearly much closer to FRB than pulsars. So meaning that the magnetar might be able to produce very energetic bursts. And there are also 2 other advantages of this discovery. One is like you can interpolate from that single burst that you are seeing one in our Milky Way up to this energy level, and you assume some luminosity function. You can say whether this one, burst from magnetar is able to explain all FRBs we see. And from that single one interpolated, it's okay. So, which means that it is possible at that time. It is possible that all FRBs are magnetar bursts. And the second thing is, the energy budget of magnetar has the advantage. Like currently, we still don't know how this is emitted, but at least magnetic energy from the magnetar can be 10 to the 47 Earth for 10 to 15 Gauss surface field. So, and magnetar are like through magnetic reconnection, it is possible to instantaneously release a large fraction of the magnetic energy. So, based on these two arguments, a lot of people started to feel happy with this magnetar model. But now, like 2 years has passed, we have more and more observation now. It's time to ask again, like, are we satisfied with magnetar as the single progenitor of FRBs? And also, moving forward, what are the observations we need to that might help us understand the progenitor? Then I'll start from some puzzles of the recent studies, which is not immediately obvious with the magnetar progenitor. One is the localization of FRBs. In the past few years, there are more localized FRB published. So what we know about magnetar in our Milky Way is that it chases star formation. So this is the galactic height distribution of the galactic magnetar, which is the distance from the galactic plane. You can see they're almost all within 100 parsec. So they're really in the plane because they're very young objects. They're less than 10 to the 5 years. And you assume a velocity of 10 to 100 kilometer per second. And in 10 to the 5 years, it indeed shouldn't move too far away. This is consistent. It's very young and in the plane. But what we see with FRBs are, first of all, some of them appear in galaxies that doesn't have star formation. Doesn't have much star formation. For example, this. Why is the resolution so low? It's not my slide. I think it's the projector. This is the recent work from the ESA group. Like this source is really in some low star formation galaxies. And also, the majority of FRB is still in the star-forming galaxy, but then you really look at the picture, where are they in the star-forming galaxies? They're really like offset from all the star-forming regions, right? In the outskirt of the galaxies. And that's not like carefully select few examples. I would say like 40% of them are really offset from clearly offset like at some outskirt galaxies. So if you interpolate this offset to some age, assuming the characteristic neutron star velocity, it has to be greater than 100 mag-year, which is much older than the normal magnetar we see in the system. This is already difficult. And another even more difficult thing is like in 2021, people find that the most nearby FRB are localized to a globular cluster, only 3.6 megaparsec away. So globular clusters are known to have no star formation. Not only they don't have star formation, but they should host old population. But also like only a tiny bit, like 0.001% of the stellar mass are in globular cluster compared to galaxy. So whatever you see in the globular cluster, you should see, if it tracks stellar mass, you should see like 10 to the 5 more sources in the galaxy, which is certainly not true in this case. So this is, I would put that as like milestone discovery. It has few important indications. One is clearly there has to be a different population of FRB that has to be dynamically formed, because it has to be much higher rate in the globular cluster, which are very dense cluster of stars and has a lot of dynamic collisions and things there. So there has to be a different channel. And the second is, this is the closest FRB, far more closer than others. So if you have hundreds or more things in the galaxies, in the field galaxies, then we wouldn't see the closest one in the global cluster. It's like you go to China and the first one you see might not be like a Canadian or something. It has to be you go to Canada and then the first person you see is a Canadian. That makes more sense. So at least in the near universe, the fraction of FRBs in the global cluster has to be reasonable. The third is, as we said before, FRB can be a probe of cosmology, matter distribution. Then the thing we worry about is like there's some contribution from the host galaxies, and you worry about the host galaxy is evolving against redshift. But if that one is in the global cluster, there's not much free electrons in the global cluster. So even if it's in the early time, then like that part of like biases will be very different. So as a cosmological probe, it's also important if you want to understand the biases. It's also important to study this population because there might be very different biases. So what can introduce this weird global cluster? So one thing, there are two things, as I said before, are very constraining. One is you have to explain the rate. You have to at least have one up to the distance of 3.6 megaparsec. And the second thing, it has to be energetic enough, whatever progenitor is. So if it is a magnetar, you still want it to be a magnetar, then it has to be a which can explain the energy. And then you have to explain the rate. You have to have a dynamic channel to form enough magnetars in the global cluster up to that distance. So you can list all the potential dynamic channels like Y dwarf merger, Y dwarf neutron star merger, neutron star merger, blah 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 blah. And you'll see that actually the only one that can stretch a little bit to reach the rate is the Y dwarf merger. It can so the per global cluster is 10 to the minus 8. And then like if you have something active for 10 to the 5 years, you might be able to see one up to the distance of MAD1, which there's only 1,000 global clusters. So all the other channels, it will be too rare. Those kind of equations are too rare to form a magnetar that live long enough for you to see it. And another possibility, for example, recently Lee is trying to push me thinking about that, is the millisecond pulsar, which is commonly seen in the global cluster. Then the rate is okay. The constraining part is the energy. So previously, people stopped thinking about millisecond pulsar is because it's difficult to reach the spectrum luminosity. But however, a few years ago, Shouxian and I had this summer student studying crab pulsar, and we find that, well, maybe the emission can be highly beamed with a large Lorentz factor. Then in that case, the potentially the spectrum luminosity can reach what we see with this MAD1 FRB. So really, this is like started to force us to think about new scenarios. And also, it's very nice because previously there are huge arguments whether Y dwarf can form magnetar. Some people think they can, some people think they cannot. And I don't think this thing can be settled just theoretically from those simulations. There has to be some observation, and this provides some new way to study some other field like Y dwarf merger, and maybe it can settle things. And another indication is those different channels has different redshift distributions. For example, if the FRBs are from normal magnetars, it should track the star formation. And the star formation peaks, like it's an order of magnitude higher at around redshift 2. And then it drops at higher redshift. So a lot of FRBs should be fine here. even if their luminosity, even if they're Euclidean, assuming Euclidean universe, they should be evenly distributed along the dimension. But like, oh, sorry, the right, this axis is the star formation density, and this gray curve is the star formation rate against redshift. And the dotted one, you should see the y-axis here. This is the Y-dwarf merger rate against. And I think I'm not plotting this properly. This is linear and this is logarithm. So if we are both in logarithm, the merger rate is actually sort of constant. Which means that if in the nearby universe the two populations are similar, then at redshift 2 it should be dominated by the magnetar FRBs. But at redshift 4 or 5, where you're concerned about, then the two populations should be like equal again if they're equal here. So what does that mean? That means like so you're very most interested in the very nearby one to study the progenitor, and you're very interested in the high redshift one to probe the amphipolar ionization. And in both cases, potentially this population can contribute a reasonable fraction of FRBs, and they can calculate lots of different stars. So it's very interesting. So this is the first thing that I think not directly in the recent years we know, and that's not directly coming to the classic magnetar pictures. Oh yeah, sorry, I forget this. So I was saying this Google cluster FRBs are an interesting population, but we only have this one detection, which is how to decide the fraction, and also which is hard to you want it to, because at a large distance, you're not able to localize it to FRBs because your spatial resolution will be getting worse and worse as the FRBs come further away. So you sort of need to know the properties from other aspects. You need a population to study the properties of this FRB for you to be able to distinguish it from other populations at a larger distance without localization. So there's this attempt to try to find more globular cluster FRBs. So there's, as I said, we find one at M81, and up to the distance of M81, there's 1,000 globular clusters. But there's this Virgo cluster, which has 15,000 globular clusters, so you should expect more sources there. So we are using FLAS to observe that the expected rate is 5 per hour, well, ranging from 0.1 to 50, assuming different luminosity function, but on average 5 per hour. We have observed it for 10 hours so far, 12 hours so far. We haven't found anything, unfortunately, but we are still doing that. The second puzzle is like a few years ago. Previously, the burst of FRB appeared to be sporadic. And there are attempts to find the periodicity, but mostly very short periodicity, like millisecond-second, because people are thinking about pulsars. But like because the chime has this even exposure, they are fixed on the floor and scanning the sky every day. So one day it's raining and I don't want to do my work, and I decide to look for longer periodicity on time. And we find one. So this is the FRB. So this line is the sensitivity, and those arrows are the time we actually detect FRBs. So they actually appear very regularly. So this gray line says every 16 days you plot these lines, and you see that they correspond very well to the observation of FRBs. So last time I see this kind of, so what does this mean? Like, this is what I searched on Google Trend, like when people search Turkey in the US. Yeah, it's appearing periodically because this is Thanksgiving. But like, why is this FRB having this periodicity? It's so strange. Oh, this is after you fold it, it actually fill in some very narrow phase range. So this is in terms of observation, it's really nice because this is one source, you know when to look at it. So you're very efficient at following up. So after we find this periodicity, the observation detection goes, like previously there's no FRB detected at this low frequency, but now they're with more confidence, they push the observation to lower frequency. And they also have very high frequency observation with some of the German students that I'm working with. And also, surprisingly, there's the active phase is different at different frequencies. So the lower frequency becomes active first, and then the higher frequency follows, which we don't understand what's going on. There are lots of models because this periodicity usually are related to some circular motion so that you can see it repetitively. So quite expectedly, you'll think about, well, maybe there's a binary, or there's the source is processing them every 16 days, processing towards your line of sight, or this source just spins very slowly. These are all non-trivial because we've never seen a magnet car spin that slow, and it not only has to be spinning that slow, but also this is one of the most active sources. And the second thing is for the precession, well, for the free precession, the magnet car, it's hard to maintain the precession. It will dissipate very fast. Both of those are not well understood, and also binaries. It's not under, well, the normal magnet car we see doesn't have a companion, it doesn't preferentially have a companion. So why would that be having this period is itself a very interesting question, and we still don't know. And also, I find some of the models very intriguing in the sense that one of the models says that it has a very close by companion introduced force precession. This tight binary will be a potential Lisa source. So it can be connected to lots of other fields. In 2021 with a postdoc in CETA, so we're trying to find a way to distinguish different models. And one of the way is the polarization. So, well, I'm trying to plot the geometry of different models are all different. Not explaining, going to details, but because of the geometry is different and the polarization are probing directly to the geometry when the burst is emitted. So for different models, like this is a slow rotation magnet car, this is a free precession, this is a forced precession, and this is against the 16-day period, the phase, and this is the polarization angle. So you can see that the slow magnet car, you will have a very thin lines at different phases, and the free precession will be blobs, and the forced precessions will be blobs, but has additional symmetry in the phase. So that German student Surya is still helping, and also we have this effort to keep trying to find more here with other FRBs, that somewhat because this one is the most active one, and also the 16 day is just precisely the time that's very convenient for the time exposure to find this. So we still don't have other very convincing ones, but we're still trying. Yeah, that's the second thing. That's not yet immediately explained with the magnet car model, but potentially can have important indication of the progenitors. And the third thing is the magneto-environment. Before I go into that, some little intro will study the magnetic field in radio wave, which I'm very into it, as my colleague knows. So we use those parameters. I is the total intensity, QU is the linear polarization, V is the circular polarization. And in the normal ISM, we have, well, here I define magneto code. It's not some, I'm just defining it to be easier to refer later in the talk. So we have Faraday rotation, which is appear as the QU rotation. But in some special regime, for example, relativistic, highly relativistic electrons, pair plasmas, or very large magnetic field, I call it magneto-hot plasma, then there will be a mixture of L and V. So take out messages. In the cold plasma, circular polarization doesn't change. In the hot plasma, circular polarization does change. So one thing about FRB is they often appear in highly magnetized environment. So those are the 3 FRBs against time. This is the rotation measure, which is integral of electron density with parallel magnetic field. And see, they're really large. So the normal pulsars, usually the rotation measure is order of 10. But FRBs, it can reach order of 10 to the 5. And there's one source that we see is a magnetar that has high RM, which is this yellow line. But that's because it's near the galactic center. It has nothing to do with the magnetar. It's because the supermassive black holes in the galactic center. And also you can see the time scale for the RM to change is much longer compared to those FRBs. So unlike normal pulsars, normal line of sight in the ISM, somewhat a reasonable fraction of FRBs localized in the highly magnetized region, which we don't know why. And it's not only highly magnetized, but also highly variant. So if you map this time scale of few months, so in few months, if you times 100 kilometers per second, it's sort of AU scales. So in AU scales, it's changing orders of magnitude. It's changing like order 1. So very strange. And not only it has large variable magneto environment, also some of the source shows structures along line of sight. So this is one of the FRB observed with fast. So the blue line is the circular polarization. You can see this oscillation in circular polarization that's proportional to lambda squared, which is characteristic Faraday rotation. But characteristic Faraday rotation doesn't affect circular polarization, as I said. So the reason we explain it this way, so it has to go through a magneto-cold region, which introduced the rotation measure. And then it has to go through a magneto-hot region for the rotation measure to lead to circular polarization. And then it has to go through another cold, magneto-cold region for it to have another RM over opposite signs. And then that will be the thing we observe now, which is surprising because I could have this region right next to the projector without problem. But having this after the cold region when the plasma already cools down in much larger scale, this is non-trivial. So how to explain that? We still don't have a very clear idea, but one of the potential hints is from the pulsar with a companion. So this is a pulsar, 1259 minus 63. It's in a 1,000-day orbit with a massive star. So and plus minus 40 days from when the pulsar is getting in the periastron, which is the closest to the companion, you can see this 10 to the 5 change of rotation measure. So near a massive star, you can introduce a large change and fast change of rotation measure. And also, this is every orbit is different. How they change is different. The second thing is, recently we observed a millisecond pulsar in the globular cluster. We call it Terzan 5A. So it's a pulsar with a tiny companion in a very close orbit. And it also shows that this red lines, so this source is having this material across all orbit. So x-axis is the orbital phase. The black dots is the dispersion measure, and the red dots are the rotation measure, Rm. So you can see there are material all across it. You can see these mini eclipses and the changes of dispersion measure. And also you can see this fast change of rotation measure of about 100 at this orbital phase. So this is indicating what is this phase is. So this is line of sight. This is the pulsar. The companion is like almost on the side or behind the pulsar. So the line of sight is really far from the companion, but you can still see this large change of Rm. That's just indicating, well, that first of all, that gave us a constraint on the magnetic strength in the companion wing. And also it indicates that, not only near periastron or superior conjunction, when the line of sight is close to the companion, in some geometry, for example, if the bow shock is facing the pulsar, you can actually see this across all orbit. So it doesn't have to be very periodic, because if the inclination angle is large, it can be across all orbit. And second is like here, when the dispersion measure actually starts to change, we no longer see the rotation measure because it's depolarized. It's changing too fast. But we can estimate, because previously we had this estimate of magnetic strength in the same orbital phase, and times this dispersion measure, which tells us the total electron. We should expect the rotation measure to change at least 3,000. So the observation of pulsar is different from FRB, which you can see single burst. Pulsar we have to integrate sometimes. So previously, the difficulty of studying pulsar, people often see this depolarization, but they don't often see this change of rotation measure. It's because they have to integrate too long and they depolarize. But actually, there can be very large Rm changes in the pulsar binary system. Okay, this is about the fast change of rotation measure. We see that with a companion, we can have large, fast change of rotation measure. And the second thing, as I said, about this FRB, we feel so confused why there are multiple layers. But this is another way, like if there's a companion, then we just naturally introduce a special region. Actually, in this source, we see the change of circular polarization. So this is the circular polarization. The y-axis is the orbital phase. The x-axis is the spin phase. So the blue and red indicating different signs. So you can see this is the phase when the companion is behind the pulsar. This is telling you the emission property of the pulsar. But when the companion gets close to the line of sight, so this is the phase, we can see blue turns red, red turns blue, means that the circular polarization flip signs. And as I said, this is something you can't explain with cold plasma. You have to get it magneto-hot. So we started to model that because this pulsar binary is perfect. We know the emission property from the phase when the companion is far away from the line of sight. And then we can ask, well, the simplest assumption, all those phases are going through the same propagation effect. How can we reproduce the data we see when the companion is close to the pulsar? So the black dots are the dots are the observation, and the curves are the model. So with 5 simple parameters, I add an absorption from the companion and a V flip from the magneto-hot plasma. We can reproduce all the frequency very well. And also we have no parameter against spin phase, but we can reproduce the wiggle very well. So in that case, I claim that, well, I can understand what's going on here because I can have this. So the idea is, how does that happen is when the companion, because this happens every orbit at that phase.
So it has to be some large stable phase. So the idea is the pulsar light is passing through the companion magnetosphere. And you can see that along magnetosphere, naturally here the magnetic field lines is towards this direction. Here the magnetic field lines towards a different direction. So there's a flipping in the parallel magnetic field. And if the magnetic field strength is large enough, the circular polarization will follow it and flip signs. And this gives us constraint of the magnetic field in the companion along this line of sight has to be greater than 10 Gauss. So at the companion surface, it has to be at least 100 Gauss to Q solvent. So we think that, well, we can understand this well, and if the model fits the data very well, we can build at this source, and we can constrain the strength of the magnetic field. Yeah, and then go to the comparison of this sources with some of the FRBs. There are lots of weird polarization behavior of FRBs that's very rarely seen in single pulsars, single normal line of sight across galaxies. But with a companion, actually a lot of behavior, you can introduce a lot of behavior with a companion. So this is good. So maybe it's suggesting some of the FRBs that can solve this difficulty. Maybe some of the FRBs are in binaries. And also that can also naturally explain the 16-day period and also the Google cluster localization, because Google cluster have lots of binaries. But even if it's not, our modeling and studying of the polarization effect can be applied to FRBs and help us understand what's happening there. Oh, and this thing, another indication of this study is, so this circular polarization, so if I only observe like few bursts from this system, because this is a very small orbital phase, I might not notice a orbital period. But if I look at the circular polarization, it's very clear that it only changes sign in a very narrow phase window. So studying this extreme polarization effect help us to look for a very special line of sight, and that might provide us more information about the circumburst environment and the environment of the system. This can be like this semi-regular, semi-periodic change in the circular polarization can be a way to find, can be an evidence for companion. So yeah, summarized here is FRBs are millisecond-duration radio bursts from a cosmological distance. They might not be catastrophic events, and some magnetar can produce some FRBs, but we still have lots of puzzles to solve, and it strongly indicates that there are other populations of FRBs and widely unexplored field. Okay, going forward. So I think Weili must have shown this a lot, and then Xiuxian made this plot. So I like it very much. So this is the sensitivity of the telescope. Going towards this direction is the more sensitive instrument. And this is the field of view. And combining those, it's detection rate. And going this direction, you are detecting more nearby FRBs. And going this direction, you are detecting more cosmological FRBs. And this is time. And I'm so impressed to see a burst, which has like similar rate as time and much less sensitivity, which means that it will detect a lot of more nearby FRBs. This is very exciting because nearby FRBs are the things where we can detect multi-wavelengths. We can perform multi-wavelength studies. So radio is really like the energy is like h nu. So radio like low frequency. You need tiny bit of energy to see it from cosmological distance, but like X-rays or something, it's really hard to see a single object at a very far away distance. And only if you have enough nearby source. For example, the galactic magnetar burst. People detect the X-ray burst like simultaneously, which is a very strong indication of this magnetospheric original FRBs. So up to like 10, so we need more FRBs up to the distance of like 10 megaparsec, 100 megaparsec, which are the like golden source where we can pinpoint what's the progenitor. And also in other cases, for example, if you have a neutron star with a companion, because FRBs are bright, it can light up the companion for a few, for a second, and then release out. You can have this optical burst. And you can detect it up to the distance of 100 megaparsec, but only if we have enough sources to test it. So I'm very excited that there's this experiment going on, and I hope it can happen in a short amount of time because there's lots of competitions. And also this is fast, so the rate is very low, but it's detecting more sensitive, deeper FRBs. So like ASIAA 2000, they are going to detect like also a high rate but more distant FRBs. Those will be a golden probe to study the cosmological application of FRBs. So very excited that like there are so many active like experiments going on, and you're involved in one of them. And not only there will be more bursts in the next few years, but there will be much better localization. So currently the published time catalog FRBs are localized to 15 arc-minute, most of the FRB published. But in the next few years, the Caltech has this effort of ASIAA 2000. They're planning to localize 10 to the 4 per year to 3 arc-second, which is 300 times better than the currently published FRB time, FRB catalog. And also there's time outrigger. They're planning to localize 1,000 FRBs to less than 50 milliarc-second in 2 years. And those will be very, for example, in terms of progenitor, we can really study the local environment of FRB much better. Like this will be the time baseband resolution, and this will be the ASIAA 2000 resolution. And among those, like a tiny dot here will be the time outrigger resolution. So previously, with time baseband, maybe for nearby FRB, you maybe know it's from this galaxy. But only with better resolution, you know whether it's in a star-forming region or something else. So I think there will be a lot of progress, and also for the more detection of far away FRBs, so FRB has this advantage that it's sensitive to basically all spatial scales. Unlike CMB, for large scales, like the primary CMB is very large, so it's not probing that very well. But FRBs is kind of sensitive to all scales. And also, it can be used to probe intracluster and halo distribution, which are like long-standing problems. So it's exciting. I think we're in a very good time to do this. And also there's only like 10% of FRBs currently with published polarization, and sooner or later we'll have more, and I think I'm also quite excited on that aspect. So to summarize, I think there are a few directions in general, like monitoring nearby FRBs, and studying the magneto-environment for more FRBs, and also multi-wavelength follow-up. And there are greater opportunities for greater communities if you're working on dynamic channels, like evolution of binaries. There are also opportunities for you to chime in to discuss those like dynamic channels of FRBs. And if you're a cosmologist, there are also exciting things to do to study the distribution of matters. And also I think the statistical technique to study it is not well developed, so a lot of room to be improved. So, and those are the things we know. my feeling is like it's not difficult to generate radio emission because they are relatively low energy. So now if you have 10 FRBs, you detect those most common channels. But you have others or more, usually you detect other more important, more interesting fact. That's what you see with like pulsar binaries. Like whenever you increase the detection by a non-orbital magnitude, you discover something new. So the previously what we said is what we expect is happening. It's already exciting, but there can be a lot more room for the unknown things to happening. So I'm really excited and hope that also very looking forward to the first project here. And thank you very much.
Thank you, Dongzi, for a really exciting talk. So any questions or comments from the audience? Yes, please.
Thanks for the talk. So in one of the earlier slides, you showed the redshift distribution for Wydrop merger rate,
Yes.
and as a comparison with star formation rate.
Yes.
So what is the reason that there is a dip in the Wydrop merger rate?
Yes. So this is the cluster formation. So this is sort of, and this is, so it's just like the star formation. It has a dip here. The cluster formation, the dip happens earlier. And here it's rising again. It's because the core collapse, the global cluster, they experience the core collapse phase. So these two are actually different reason for the rates.
Okay.
Yes.
So that means if this prediction is robust, then there's still kind of like factor 4 modulations on the number density.
That's true. That's true.
Right. So have you
Yeah, but
looked into the data?
it's not this like star formation. It's an order of magnitude increase. It's yeah. But and also, I feel that this one we really have to distinguish these two populations. Otherwise, what you see is the combination of these two lines, and it wouldn't be so obvious. And currently, I think probably later on when we have better localization, we know the redshift distribution better, maybe there's a chance for us to look for the distribution change, yes.
Yeah. Interesting. Thanks.
So I have a question. So you are looking for the burst from the Virgo A globular clusters.
Yeah.
And have you tried checking whether charm has some detection from that direction?
No, and I also don't expect chime to see things. So the rate we estimate is for fast, which is 200 times more sensitive than chime. And the second problem is there's a very bright black hole in the Virgo A. It's this event horizon telescope that they're watching. They're super bright. So for chime, the beam is 0.25. So basically, the whole thing, a large of them is covering the black hole, and it's the sensitivity is very low because the black hole is served as a very strong noise. Yeah, but for fast we have this 19 beams, so basically I'm deserting all the central beams.
Are there any closer global cluster that we can observe?
There are. I think that one is by far the one with the largest number of the global cluster. But there's a nearby one with 5,000 global cluster. I think it's most optimal to observe it with Meerkat.
Meerkat.
Yes. But the expectation is you have one fuse or one plus, three plus. So I kind of feel that because it's so non-Poisson statistic, it seems more optimal to observe sources with potentially more sources rather than potentially more expected bursts. But I think it will be a nice, interesting project to observe that with Meerkat. And Meerkat has open call. Starting this year, that's the first time they have the open call for the FRB backend, FRB puzzle backend. So it's an opportunity.
Any other questions or comments? If not, it's close to 3:30 or 30, so maybe we can thank Dongzi again. And just a advertisement.